Hello, my name's James Taylor and welcome to another episode of Invalid Entry, and it's Pi Day, as you can see from this very weird layout and the fact it says Pi Day right beneath me. Today we are going to be calculating pi. Lots of people on the internet like to calculate pi in different unique ways on Pi Day, and I am going to use a rather trivial method today called Buffon's needle problem, which was invented by a man called George Louis Leclerc. Not Buffon. He was the Comte de Buffon. If you don't believe me, here is a picture of him. As you see, he's a very posh gentleman. I wish I could pull that off. The nice braid. But I think I get laughed at if I wore that these days. However, he was one of the people who invented this problem, and it was one of the first geometric probability questions asked, which was basically, he had a thing called Buffon's needle problem. Here we go. There's the maths underneath. And basically it turns out the question is, if I drop a needle on a strip of wood, and he probably had a wooden floor, you know, one of these old-fashioned wooden plank floor, if I drop a needle on it, what's the probability that the needle will cross the line versus sit inside of a plank, no matter what angle it falls at? So he was like, I'm not saying angles always 90 degrees, always straight on. He's saying it could angle at any angle you like. And it's quite a complicated maths puzzle because you've got lots of variables here. You've got the length of the needle and you've got the width of the stripe here. For this experiment, I'm using 2.75 inch long needles and 3 inch stripes, but he wanted a generic answer for any length needle and any length stripe. And then he was like, well, there's also an angle it could be at and the distance away from the line. And when you start breaking the maths down a little bit, you realise this is quite a complicated problem. It's quite a fun problem. And pi is involved. The probability has this relationship with pi. Or so we hope. And you might sit there going, well, we're going to do the experiment. And what I'm going to do is I'm going to drop them on. I'm going to drop on a bunch of needle. I'm going to drop on one less needle than that now. So just threw it at my face. A bunch of these plastic needles onto this. If they land like that, I'm going to put a counter in the bottom here. If it lands across the line, I'm going to put a counter on the top line. These are infinitely long lines, so if it sort of lands off the top here, I can just project the line forward and say, yes, that crosses and that doesn't. If it lands over here, this one doesn't count because this isn't wide enough. So it's only these three. This side does count, but this side doesn't count. So I'm going to drop these on now. And I'm just going to see, as you see, they sort of bounce around a bit. I'm sort of dropping them end on, so they sort of fall one way or another to try and stop them all being horizontal. And we should get some answers coming out of this. So I count this as that's crossing, I think. 1, 2, 3, 4. 4 crossing. And 1, 2, 3, 4 not crossing. So I'm going to put 4 and 4 in here. And you see my calculation is coming out. So I've got two numbers here. This is the value of pi we've calculated, and this is the value of, this is actually the delta away from what we think pi actually is to some level of accuracy to give us sort of that. So we're about 0.5 out at the moment. I've designed this spreadsheet to allow me 3 attempts, but it's going to add up across all 3 attempts. So the more needles you drop, the more experimental errors begins to waver away, because you could just have everything, you could end up with all your lines exactly like that, and obviously that's not, it's possible, but it's not realistic. So the more you throw at this, the more likely you are to get a value near to pi. And already we're seeing a lot of things cross here. Wow. That's going to completely break my figures here. There's only one which isn't crossing here, so I'm going to put 1 there. So you've got 1, 2, 3, 4. Actually, there's 2 which aren't crossing. I'm going to put 2 there. It's been knocked, obviously, but it counts. 1, 2, 3, 4, 5, 6 that are not. Okay, so that error has come down. I think it was 0.4 before, but now it's 0.2. It's obviously dropped below pi at this point. That's fine. You can have experimental either directions. So pi we currently think is 2.9333 reoccurring. A little bit out. I know some people are going to accuse me of having placed these needles, but I assure you I am doing the best of my ability. Right, we've got one over here I need to redrop because it's way outside. I don't know if that's in. That's now off. Right. So we've got 1, 2, 3, 4, 5, 6 on the lines. So we've got 6, which suggests that we have 2, 1, 2 not on the lines. Okay, we're now 0.39 away. I was hoping to be closer, so what I'm just going to do is I'm just going to do a fourth batch really quickly. Okay, maybe fast forward this. So yeah, you're sort of seeing it's actually heading to and from pi. If we do it long enough, if we get good answers, we would end up with pi to some level of accuracy. So a little bit disappointing that I ended up with pi as 2.75. Please go back and fix all your geography textbook or your geometry textbooks. Geography textbooks don't generally care what pi is, except for its distance to the bakery. Now let's swap to some actual simulation code and see how well this actually works. Before we do, actually, I want to talk about how this actually works and how we end up with pi. The main thing that you think about is you start thinking about how the needle looks like it falls. You can start simulating this as you pick an end, and then you can work out the other end of the needle, and you begin to think, pi might be involved, because as you rotate that round, you see it makes a circle. So what we actually do is we start thinking about the end, we think about the middle of the needle, somewhere like here, that's where the middle is. So you can sort of imagine that the end of the needle traces a circle around that point. Now I only ever care about half the circle because I only ever care about the closest line. If your needle was on the other side or over the halfway point between two stripes, then you begin to actually realise that it's just the same symmetrical. So I only here for this distance out, this is the area or angles or the number of angles which it works for. You can actually reverse that and think about, well, actually for different angles, what is the area which the needle actually, if the center point lands on, does it cross for different angles? So you can imagine for a sort of a box like this that there is a circle here where if the center of the needle lands inside that circle, but this is for angle straight up and down sort of thing. So this is angle 0, and then here is angle 90 degrees. And what you're really looking at up to the halfway line is sort of this quarter, is the ratio of the area of this to the area here, where the height of this box is half the width, the length of the needle, and the width is half the width of the entire thing. So you start noticing, because this is a circle, a badly drawn circle, pi is going to be involved because pi is involved with the area of the circle. So what we're saying is, what's the probability for these different things? So you end up with two integrals going on, and really that's what, when you look at the web page here, he shows, yeah, you've got a double integration going on, showing that, yeah, you've got these, instead of dealing with degrees, you deal with radians or and it pops out. So you end up with a formula for the probability. You see there's the circle sort of showing up there, which is 2L over T pi. Well, L over T, we have that as a fixed variable for this particular experiment. It's 2.75 and 3. So you end up with the probability equals a fixed thing, so you can sort of divide that by the other one and come round, so you end up with pi equals that. And that's really what's in this formula here, is the reverse of that, saying we'll take the probability, the measured probability, the empirical probability of it landing, and actually reverse that on. Now, for any given day, any size of stripes, any ability to actually drop needles in a truly random fashion, you'll end up with different values. But I'm going to swap over now and show you actually a simulation of this, and you'll sort of see it drop out, and you'll see pi involved with that. Okay, so we haven't done any live coding for a while, and I'm looking over my notes about this, and they're going, yeah, this is going to be fun. So don't worry about my imports, they're just so I can do some visualizations later. So I'm going to simulate length and width. Now, when I did my simulations before, I actually simulated a whole bunch of stripes. So I'm going to do the same thing here. So total width, I'm going to pass in there as a sort of a board. So you've got to imagine there's a board of a certain width. I don't really care. So on my bit of paper, this is the width, the total width. I don't care where up and down, so you can imagine it being infinitely long. I only care how far long it is and whether it crosses an individual one. If you want to make a simulation faster, you don't actually need to do the total width. You only have to simulate to the closest line, so it lets you pick much smaller range. But I'm going to simulate the entire thing because I did it already. So my start width, I'm going to simulate it from the end of the needle. So I'm going to pick the start point. It's going to be random.random times the total width. Okay, and then the angle I'm at is going to be random.random times math.tau, and that picks me a random angle all the way around 360 degrees. And for those of you who know what I just did there will be yelling, but that there makes it all invalid, and it doesn't. That is actually what we're doing. So unfortunately that is the case. Now there is an element of this in that I'm using numbers in the computer program, so I don't actually have a full sort of jump because of the accuracy of the number of bits in a floating point number, i.e. specs and all that. But it's going to be accurate enough to do the simulation. But that there is the hint as to why pi drops out in the first place, because tau is actually 2 pi. It is the definition of it. So the end point, on the other side, or rather the end width of its component of it, is equal to the start point plus the length times math.sin angle. Very simple. And then, so the start stripe, the question is which stripe is the start point in and which stripe is the end point in. And we can do it really quickly by dividing by the width of the stripes. So we can say which stripes it is in. The 0 is the first, second, third, 0 indexing of course, and the end stripe is equal to the end point of the width. Okay, so what we can now do is if the start stripe equals the end stripe, then we can say that it doesn't cross a stripe boundary. If they're not the same, then it's crossed the stripe boundary. It's either one before, one after. So we can return naught, else return 1. So there should be some semicolons there. How about that? So I can now simulate a 3-inch, 2.75 long needle on a 3-inch stripe of 10 inches wide, 20 inches wide, and that needle crossed the boundary. That one crossed the boundary. That one didn't cross the boundary. I'm glad that did it after only 3 attempts, because otherwise it gets a bit boring. So we now have the ability to simulate this in a way which makes sense. I actually am going to cheat here, and I'm going to bring in from my pre-script thing a whole bunch of widths, total sizes, length of needles. So I've got a few at 10, a few at 8, just to show that this probability works no matter the size of the thing. I've sort of typed 10,000. It doesn't matter. Like the probability just affects itself. Okay. I also wanted you to just bear with me as I just set up my canvas. Okay, so I've got a canvas here which has nothing. Now I'm only showing the probability. I haven't got anything in here. So the samples we're going to do is we're going to do 1,000 samples. So each one of these I'm going to sample 1,000 times. So for test in inputs, which is those tests there, cost equals 1 and total equals 1. And the reason I have to do that is because I get a divide by 0, otherwise I don't want to deal with that. So for I in range samples, so we're going to run this test a whole bunch. We really are going to run a whole bunch. What I want to do is not do that. We'll see how it comes out. We'll do ax dot. Ooh, I should have done this beforehand. We're going to do crossed plus equals. We're going to add the simulate, we're going to take the test length, we're going to take the test height, we're going to take width actually, and the test height, which is actually the total width at that point. And we're also going to add one to the total, just so we know how many we did in total. And that ran 3,000 in the blink of an eye, which is great. If I percentage 10, just so every 10th one is what we're going to do, is we're actually going to calculate pi-ish, that, or pish as we're calling it. It is equal to 2 times the test length divided by test width. Just got to make my crib a little bit longer. Times by crossed over total. And I realised I could probably simplify this and move some of these to the top and all the rest of it. And I use lots of brackets here so I know what the hell's going on. And ax dot plot I, comma mine pi-ish marker. I'm going to put that as a nice plus, and then I'm going to put the colour is equal to the test colour. Okay, so very quickly now we have all these numbers converging. You see, we were only doing 10 or 30. See, the range of numbers here was quite high away from pi. If I actually introduce the pi line here as ax.hlines y equals math.pi x min equals 0, x max equals samples, line styles equals hyphen, line width equals 2. All this is just matplotlib, color equals k. Make it black line. Obviously k is black. You can see there's where the pi boundary actually is, and these are now getting closer and closer, or they sort of descend towards that pi line. Some are a bit early, some are a bit high. Run that again, get different sets of answers. Here the green, the blue one, the green one, the blue ones are actually 10 wide, 8 ones. They're getting very close to pi towards the end. In fact, they're very close to pi here as well. So you sort of see this experimentally, there is experimental because you're dealing with random numbers and sometimes it diverges a long way just to prove you wrong. But yeah, if you run this enough, you will eventually end up with a more and more stable pi. The reason it gets stabler is because if you have a lot, like a sequence of ones which cross the line or a sequence of ones which don't cross the line, it really will only impact the ratio a little bit as you have more and more in the total. So it gets more stable as you go further out. So it will tend towards the line and tend to stick on it in a better way. So it's harder for it to diverge as it goes further away. And so yeah, this is a repeatable experiment where you end up with pi coming out of it. As I say, it should be obvious here because in my simulation it's more obvious because here I'm inserting pi because that's actually math.pi times 2. If I bring that in there, then my simulation comes out looking exactly the same every single time. It comes out coming out as 3.14 plus or minus a little bit. You do need to run the simulation. This is running 1,000 simulations. It's actually running 4,000 simulations back to back. The measurements you use don't matter. It doesn't matter if you measure in centimeters or inches or feet because it's all about the ratio of the two distances and the angle they drop at. And so yeah, it's not surprising pi falls out. This is a bit of a special video for me, so there's a little bit of Python involved here with just simulating it. And it's more of a fun thing. It's more one of those fun little things. So if you want more videos, please hit like and subscribe and see below for other things going on the channel. And yeah, I hope you all have a good Pi Day and eat lots of pies. Just before you go, there is one more thing, which is I want to demonstrate who ate all the pies. And this is one of my favourite news stories ever. It's from September 2004 on BBC. And the question is, who ate all the pies? And the answer is Norwich. Norwich ate all the pies. Tesco's did some research on where they sold the most pies per head, per capita. There's no information on this news article at all about what kind of pie it was, whether it was savoury pies or apple pies, sweet pies, dessert pies. No information whatsoever. We ate an equivalent of 14.8 pies per person since January up till sometime in September. I guarantee in that time period in 2004 I ate a lot more than 14.8 pies across the board because I like pies. So yeah, this is one of my favourite news stories to ever have. It was obviously a slow Friday. It came out on a Friday. It was obviously a slow news Friday back when times were innocent, and this was the quality of the news. Was we're going to have who ate all the pies? Me. I ate all the pies. So I hope you all have a good pie day. I hope you all get a pie of some kind, and think about some nice fun maths puzzles while you eat it, because I'm going to go have a pie now.